Hi, good afternoon everyone. We're here for Laboratory 2 of Mechanical Lab 319, and this follows directly from the lecture that we just had. The lecture was understanding what the process is of taking data that exists as a physical quantity somewhere in the world and turning it into a number that exists for human beings to interpret and analyze. So we spoke about that in a sort of top level, almost sort of holistic sense, thinking about how we do that as human beings, interpreting, writing things down, and then we introduced the concept of an analog to digital converter, and then we spoke about how fundamentally we're taking something that is continuous in both time and value, and we are discretizing them both. So we're discretizing the time through the sample rate, and the sample rate is the number of samples that we take per unit time, normally per second. And then the value is similarly discretized according to the bit count and the encoding scheme of the analog to digital converter that we're going to use. We don't need to go into too much detail about the discretization of value using the bit count, and the way that we're going to sort of simulate that in this class is a little bit of a simplification, but that's what we do as engineers. We simplify things such that we can reproduce the salient phenomena. So obviously, with everything being under lockdown, this isn't the ideal situation for many reasons, because this lab originally existed with you guys coming in using the function generator and the oscilloscope to look at continuous signals, and then to actually sample and analyze them with an analog digital converter. And there you would understand things like the significance of the Nyquist criterion. So we can remember the Nyquist criterion is the frequency that is twice whatever you're trying to sample. Sorry, that's the Nyquist frequency. The Nyquist criterion is that we have to sample at least at that Nyquist frequency. So that's twice whatever we're trying to sample, or otherwise we lose the frequency information of what we're trying to get. So in lieu of that physical laboratory, we're going to simulate that. And we're going to use Python to simulate it. Two reasons for this. One of them is because I can't draw those repeat sine waves very well, as you learned during the lecture, and it's not really that instructive to keep drawing things and try and just emulate it through my own drawing. Secondly, because it's a really important skill for you guys to learn. So if, as an engineer, you don't understand the systems that you're using, then you are prone to mess them up. You're prone to make mistakes, and you're prone to make assumptions, erroneous assumptions, about what you're using. So I've got one good image which I'll just bring in here. This is an image, it's not particularly clear on screen actually. I think let me just adjust the resolution of my iPad, 1 second. There we go, you might be able to see that a little bit better. So this image is of some simulation that I did of what's called a pulse width modulation. Back at my previous job, we were having issues with lots of funny electrical noise occurring, sampling data from a set of instrumentation that was attached to the end of a shaft on a motor. And the electrical noise that came up was baffling in its characteristics versus both rotational speed and then versus the actual, so it was first rotational speed and then the frequency that we were looking at there. So I simulated what the way that the motor worked. So these AC motors are driven by what's called PWM, or pulse width modulation, and it transpired that if the carrier signal was somehow getting into the system and somehow being sampled, then we would have seen electrical noise that was of the form that we were experiencing. So through a simulation of the system, just from a rudimentary understanding of how all these things joined together, that enabled us to understand the phenomena we were seeing. So these skills are really important, and that's what I'm trying to teach you guys with this simulation. So remember, what we're trying to do is we would like to have some function versus time, and we would like to have a continuous harmonic signal. This would be my continuous signal. And that would have a period of t here. So that's my continuous signal. We've got to be able to produce something that looks almost continuous using Python, and we're going to be able to do that We obviously can't produce anything that's perfectly continuous because computers aren't particularly great at dealing with continuous quantities, but we can figure out how we can produce this. What we then want to also determine is we want to take a number of samples at a fixed sample rate. Okay, so the sample rate is going to be 1 over the time between when these samples were taken. So we want to be able to do this. This is going to help us understand the effect of sample rate, because we're going to then see if we join these together whether we've actually managed to produce a good reconstruction of the original signal using these sampled points. We're then also going to have a little look at what happens if we change the bit count of our ADC. So remember, the bit count of the ADC is just the number of switches that it can store numbers as, because the ADC can only store things as a finite number of values. So we're going to look at some code that will help us sort of emulate that behavior. So let's get rid of this and let's move over to a new Jupyter notebook. I'm expecting you guys to code along with this exercise. So we've got a good new Jupyter window. I've just changed the color scheme so it's light on dark so you guys can see what's going on. I'm going to be sending you all some questions at the end of the week that are going to assume you have this notebook working. Going to assume that you can do everything with it. So you're going to be given a unique frequency to sample at, and you've then got to try and do different things with it. You've got to try and sample below the Nyquist rate, above the Nyquist rate, and I will then want you to demonstrate the phenomena of aliasing and attenuation, those things we spoke about in class. So I'm working over here and I'm going to write everything from scratch as we're doing this. So the very first thing we do, we import some packages we know we're going to need to use. This is a very noisy desk, by the way. I apologize if those noises get picked up on the mic. I'm doing my best to try and process the audio using Adobe after this. We'll see how that goes. So we're going to import, we always import NumPy, that's always handy. Import NumPy as NP. And for plotting, rather than using matplotlib, which is useful for producing sort of publication quality images, I like to use something else called Plotly. Plotly is useful because it helps us play around with graphs when we built them, and the syntax for it is a little bit confusing, so that's why I'm not teaching it in class. You're free to do this using matplotlib, but I'm going to use Plotly, and I'll include all of the syntax that you need to use and understand it. So I'm going to do import plotly.graph objects. So that means we've then got this geo. Geo is this object that is plotly.graph objects, and that's going to enable us to do some fancy plotting. So what do we want to do? So we're going to produce a figure at the very beginning, and we're then going to want to have one function. I'm going to write this as one function called make and sample. So that make and sample needs to know a few things. It needs to know what the frequency of our continuous signal is. It needs to know what the amplitude of our continuous signal is. It needs to know how long to simulate that sample for. So I'm going to suggest that we look at that in terms of how many periods or how many wavelengths we do. We need to know the sample rate that we're going to sample at, and we need to know the bit count. So there should be a function with 5 inputs that we're going to create, and I'm going to call that make and sample. So I've started a new cell here. I'm going to say that does all the things. Okay, this is not particularly great commenting. That's just how I'm writing this code as we're going along. So I'm going to define make and sample. And we said we wanted it to have 5 inputs. Okay, so frequency in is the input frequency of our continuous signal, and I'm going to give this a default value of 1 Hertz. Okay, so this is going to be in Hertz in here. And if I were writing this code for other people to use, and if I was writing this to be published, I would put what each of these inputs is in the comments below, but you guys can do that on your own. The amplitude, I'm going to give it an amplitude of 5 units. We don't care what the units are in this case, they are 5, whatever the units we're looking at. I'm then going to suggest we look at 10 periods. I'm then going to sample it at 2 Hertz. and I'm then going to say that our bit count, let's say 16. That's the default bit count that we're going to look at. No, let's change that a bit actually. Let's change that to a 3 bits because otherwise we're not seeing any changes. So this is my function down here. So we need to put code in here to create a continuous signal and then sample it. So we're going to do all of that in here. Let's put that here. Okay. So the very first thing that we're going to do is, given a, I can't actually see where I'm pointing on here. Let me just make my screen a little bit larger over here. Okay, so I can just about see where I am. So this function, when it runs, it knows that number n, I think I'm pointing to the right place, tells it how many periods we need to sample for. So the combination of the input frequency and n is going to give us tells us the total time that we need to sample over. So let's put it in here. So the period of the input signal, so t in is going to be 1 divided by the frequency of the inputs. Again, and I'm assuming you guys have gone through my Python tutorials already, but if you haven't, because you're whatever reasons, then these here are all the inputs to my function, and if I don't provide any values to them, these are all the default values as well. Okay, so this gives me the period of the input signal. That's the input signal period. And then I'm going to say that the end time, so we'll say t end, which is the time that we need to go to, is going to be this number, whatever the period is, multiplied by n, which is the number of wavelengths that we need to sample for. So that's going to be t in multiplied by n. So that tells us how far we need to go, and let's just say print so that's syntax that you should be happy with, and all I'm going to do is try and run this, and the function doesn't do anything yet because it's now created this function, but we haven't told it to run it at all. So anything that's indented here is in the function, and I'm just going to write below, let's just try and run it, make and sample with the default values. And if I do, it says the signal should be simulated from 0 to 10 seconds. And that's correct because it's got a default of 1 hertz. So the period is therefore going to be 1 second. And then it's telling it to do it for 10 periods. So if I change any of these, I can just change the values down when I try and run this. I'll say, let's make f in 2 hertz. And I would then expect this to be 5 seconds. There we go. The signal should be simulated from 0 to 5 seconds. So we've done that correctly. And this is helpful to sort of test code as you're going along to see if you've managed to do things right or not. So in fact, I'm going to put a little flag up here. I'm going to say verbose equals true. And all I'm going to do is print these out when I'm running this. And this is going to enable me to keep all of these in here and then just turn them all off at the end by running these. Because I'm going to print these out. I'm going to print different things to screen that helps me understand whether this code is working or not. So we've determined the time now. Now we need to be able to produce a continuous signal. So we can't produce a continuous signal. Well, there may be ways of doing sort of this analytically using Python. What we want to be able to do is we want to be able to produce a plot that looks continuous to the human eye. Okay, it looks continuous for our purposes, which means we need to produce a sine wave that has effectively so many samples in there. Let's say 1,000 per period. That we simply, that's good enough for our purposes. So that's the next thing we need to do. So we're going to make a time vector. So our time vector is going to extend from 0 up to t end. And the time step needs to be such that there are 1,000 of them within each period. So we'll say dt is equal to t in divided by 1,000. That's our time step. And I'm then going to make a vector. So I'm going to say time, spelled time correctly, is equal to mp.arange. I'm going to go from 0 to t end And I'm going to go in time step of dt. Let's just try this. And I'm just going to show you something. We'll do print time. Here we go. So it's printed out the time vector, that new thing we just created. It goes from 0 all the way up to not quite 5 seconds. And that's because the way arange works, it says, here's my start point, which is included. Here's my end point, which is not included. So what I'm going to do here is just change this to plus dt. And this now goes to 5 seconds as we expected. I'm going to get rid of this because I don't need this time to be printed out repeatedly. Again, with this problem, there's about 1,000 ways you could solve this problem. There's many ways you can skin a cat. But the way that I'm going to choose to do this, I'm going to make a little sub-function inside here that then that effectively is my sine function. So I'm going to have a periodic sine function in here now. So I want a signal of the form ft is equal to a multiplied by sine multiplied by 2 pi f multiplied by t. Okay, so f is my frequency in hertz, 2 pi is just there such that if we effectively this sine thing only works if we have frequency in radians per second. So we remember that omega equals 2 pi f. So we remember that's how this works. Okay, so I want a signal that looks like this, and I'm going to need to use this twice, at least twice, because I want to then put my time vector in here, and I'm then going to say, okay, I've got that. I also then want to put my sample times in there and get values out. That's the way I've chosen to sort of solve this problem. So I'm going to make a little function in here called my continuous signal. So let's say make. So we're going to make a function for the continuous signal, and let's spell continuous correctly. So we'll say my continuous signal. No, that's not how we do functions. I'm going to say def my continuous signal, and the things that it needs to know are the frequency and the amplitude. Those are the only two things. Okay, so it's fin, which fin is provided. It's been given to us already, and so is the amplitude. So that we've got those two there. And all we need to return, I'm going to get it to return a multiplied by np.sine, and then let's put np.pi multiplied by 2 multiplied by fin multiplied by t. I need to put t in as well, that's why. Okay, there we go. So my continuous signal now, so if I run this, nothing will change. I've now got an object in here called my continuous signal that if I supply frequency, amplitude, and time, it will then return a vector of values. So let's try and run this. So let's say produce the continuous signal. Bear with me 1 second, I want to check how I solved this yesterday because I know it worked, and I want to just check that I'm doing it the same way as I did yesterday. That's fine, okay. So produce the continuous signal. I didn't necessarily need to include these fin and a in here because actually they would have been available to the function anyway. Let's try and get rid of these actually. Okay, I'm going to get rid of these because fin and a are still available to this continuous signal anyway because they are all within this same namespace. So let's try and, there we go. So the only thing that I'm going to want to change is time here. So I'm going to produce this continuous signal. So I've got my object that creates the continuous signal, and I've got my time vector. I really can't see where I'm pointing. My time vector here. So if I now provide that time vector to this object, I should get an array of values. So we'll say continuous values is equal to my continuous signal, and I'm going to put my time vector in. Let's try and run that. It seems to have produced something. It's not thrown an error. So let's see if we can plot this. So we're going to start plotting them out. So we'll do make a graph. So I'm going to do go.figure. That produces a figure And let's give it a name, so we'll call it my figure. My figure is go.figure, where go is that plotly.graph objects. The syntax for adding things to graphs using plotly is a real bastard, so I'm going to just check what I wrote yesterday. I'll do it from memory. But this is not stuff I've taught you. The way that you've got to do it to a plotly graph object, you've got to add a trace and you've got to tell it what sort of trace it is. If you want to look this stuff up, I encourage you to Google, go and say, search for help with plotly. Okay, I'll encourage you, and you'll see when these plots come up why I like to use them, because they are cleaner looking and for sort of online purposes than using Matplotlib, and they're interactive, which is really useful. If you've been to my website, aircraftflightmechanics.com, all of the graphs on there are made using plotly, which means that on the website you can zoom in on them, you can peer around, and you can change things. Okay, so enough advertising for that company. So we've made the graph. Now let's add our continuous signal. So let's do my figure.add trace. And then I'm going to do go.scatter. Needs to be a scatter graph with a capital S. And then let's say x is equal to time, y is equal to signal. No, y is equal to continuous values. And its name is continuous signal. There we go. If I run this, doesn't like it. Oh, it's because that ... I think is the wrong syntax. Yeah, ... is Python. Sorry, it's MATLAB syntax, not Python. The / there just allows me to put a line feed in and continue this line down. Doesn't like this because I've used a word continuous as a variable name, and it's a word that I spell incorrectly a lot. Okay, so if I run this, I just rerun that cell. It's not throwing an error, but it's not done anything yet, and that's because it's made this figure, but it hasn't actually displayed it yet. So we'll put in here, display the figure. We'll do my figure.show. Run that. Is it going to do anything? My computer's doing something. Oh, it's just running a little slowly because this is not a very good computer. So we've now got our continuous signal here. Continuous signal, nothing really on here just yet. So let's add some things to this figure that help us sort of understand it and peer around it. Okay, so let's do my figure dot update underscore layouts. Now this, I can never remember how to do this, but I have to search for it when I do it. Okay, every time I do this, I'm going to update layout. Sorry, I'm going to say x-axis underscore title, time divided by seconds, y-axis underscore title equals ft. There we go. So it runs this now. Hasn't put. Oh, it's because I updated the figure before I showed it. Let's switch these two round. Here we go. Run this now. We've got our continuous signal on here. Okay, so we've got a continuous signal, and then we'll see if we change things around. Well, this is going from 0 to 5 seconds. It's got a period of half a second, which is right because this has got a period. This is a 2 Hz signal. Let's change the name of this. Okay, let's include that in there. Continuous signal. I'm turning this into an F string so I can put some values in. I'll say this is a sine 2 pi times ft. No, let's say, yeah, that should work actually. Let's try this. Oh, that's why. It's because it's f in. There we go. Hasn't got the name on here because there's only one plot on it, so it doesn't need a legend yet. I think that's why. unless perhaps this figure is just too wide. Maybe doesn't have the legend. I was expecting it to show a legend here, but let's add some more things and see if a legend gets produced. So, unless there's a, do I have to show the legend? I don't think I do. I think it should come on when I put a second graph on there. So we've now managed to produce this continuous signal. Now, the reason I like Plotly is because you can zoom in on here. So you can click on here, you can zoom in as much as you want. And we can see that for our purposes, this looks like a continuous graph, just because there's so many data points that it's almost smooth at every level we could possibly zoom in. If you go up here, you can just click Reset Axes and go back to our original signal. So we're almost there. There's one thing that's not quite right with this, okay? So this is going to produce our continuous signal, but no matter how many times we run it, it's always going to start at time 0, value equal to 0. And that's because we are still simulating the signal, but we're not simulating the fact that if this was in real world, that signal will be going for, time before we started sampling. So we need to add a small offset in here. So I'm going to call this time. Let's call it T0. T0 is the time offset. It's going to be np.random.rand. .random or .random.rand. Well, let's try it. I can't remember which one of these it is. I want to introduce a small decimal number that's going to be the output. So I'm going down to the bottom and I'm going to try print numpy.random.rand. Yes, that gives me an integer. Sorry, it gives me a decimal offset. Okay, so anytime you run this, it will give you a small decimal offset, and that means that up here, I can have that here. There we go. So if I now run this again, all I've done is I've said, in the continuous signal, add this T0, and this T0 is going to be decided every time I run this. So when I try and sample using this same code later, it will have that same time offset, which is the important thing. And we can see now, the first time I run this, it no longer has a starting value of 0. Second time I run it, something different. Third time I run it, something different. Okay, so we've produced something that's able to better simulate what we would have actually done in this laboratory. So let's add more things in here. Displaying the figure is the last thing we want to do, so let's add some more things in. So we'll try now sample the data. So our sample rate is set up here. This comes in, it's sample rate of 2. Okay, so that means that's our, well, it doesn't matter at all, which means we're going to create a new dt, create a new time vector, starting at 0, going up to the same end value, or going up to near the same end value, and going in a time step that is 1 over the sample rate here. Okay, so I'm going to say dt samp is equal to 1 divided by f samp. And then I'm going to make this new time vector. I'm just going to copy this line in here. Time samp equal to a range we're going to do the exact same thing now. So if I run this, nothing's changed, but I've now got a new set of times that I can then put into this continuous signal, and it will give me out the new values. So we'll say that's my time samples, and let's say sample values is equal to my continuous signal time samp. Okay, and we're then going to plot this on there. Well, let's just copy this on here. Okay, so x is going to be now time samp. Y is now going to be sample underscore values. And then we're going to say sampled signal We're going to put the sample rate, and we're using an infinite value resolution. Run this, doesn't like that. Why doesn't it like that? Oh, it's because I've not closed out this bracket up here. Okay, so this error, you'll sometimes see this come up and it's a bit confusing. So this error's come here, it says there's an error in line 44. Line 44 is actually this myfigure.update layouts. Now, the error is not actually with that line. The error is because it's gone down here, it's run this line, it's got to the end of it, and I never closed these two parentheses. So it still thinks that line 44 belongs somewhere in here. It's trying to do something with that graph object.scatter. So I'm gonna close these two, run it, and it don't work. Sample values is not defined. That's because if I define sample values with a lowercase v, let's just change this up here to an uppercase V. Okay, look at that. So that has, by happenstance, managed to, is that working? Let's try run this again. Well, there's something not quite right here. Let's have a look. So starting at 1, now my sample rate doesn't appear to be quite large enough. Oh, okay, I see why here. Something's happened with my F in, I believe. Oh, that's why. Because I don't know why this happened, because every time I'm running this is correct. It's because I changed make and sample down here to have a sample input of 2, and I'm sampling it now at 2 Hertz, which is now the note, which is now below the Nyquist threshold. So we'll say F samp is equal to 4 here. I was really concerned I'd messed that up. Let's try this again. There we go. So if I now sample at the Nyquist rate for a 2 Hertz signal, this is my output. Okay, I have an output that I've got my continuous signal, which is the blue curve, and we can see that if I zoom in, it shows where these are plotted, it shows where these points are. Okay, so I can get rid of each of those points, which is useful. That's why I like Plotly, because you can mess around, you can get rid of different points. So what we can do here is we can start playing around with the number of samples. Let's say take this up to n equals 50. And let's change the sample rate to be just slightly larger than the Nyquist. So I've got a 2 Hertz signal, I'm sampling at 4.1. And if we run this, here we go. So we see some sort of interesting beating occurring. Let's get rid of the continuous signal. We can see that our amplitude is changing heavily as we go through this signal. Okay, original signal, sampled signal. Okay. So we got this, and I want you guys to be able to sort of play around with that, and you're going to be receiving some questions at the end of the week to give you a frequency to change, a sample rate to change, or just tell me maybe whether you're sampling at above or below the Nyquist rate. So let's have a look here. Let's change this to just below the Nyquist rate. Let's change this to 3.8 on a signal of 2 Hertz. Now, if we looked at the, let's change this to a little bit below. Let's change this to 3. Now, I'm not quite seeing aliasing occurring there. There will be editing long enough, but here we go. So, yeah. Okay. So what we can see here, let's zoom in on a subset here. Here we go. So this will end up producing a different frequency, and what I'm going to ask you guys to do is try and see if we can determine the frequency from these graphs. Okay, so that's an exercise for you guys to try and figure out by looking at the peaks, say, of the reproduced data. Let's get this out and let's zoom out a little bit. The frequency here would simply be take two peaks, or take the average distance between each peak, and then do 1 over that. Okay, that's a real crude way of determining the frequency. We're going to look at some smarter ways of doing that a little bit later in this course, but I want you guys to have a look and see if you can figure that out. So we've done almost everything we need to do to simulate our ADC. There's one more thing we need to do now, which is to go from these values which are infinitely resolvable in values. So let's just change this to a sample rate of 10, something well above the Nyquist rates. And let's take the number of these down. Let's take this down to 10 samples. Let's take this to a very high sample rate now. Here we go. So if we have this now, if we have a very high sample rate, if I zoom in here, okay, we are able to capture pretty much all of this curve here. We see if we got rid of the continuous signal, for most of this looks still like a good sine wave. And that's, in here I wrote infinite value resolution, and that means we haven't yet introduced the limitation of the analog to digital converter. So the ADC can only score a discrete number of values up and down, or in terms of the value. So we're going to see if we can figure out a means of doing that. So let me just hide this one a second. Now, the following, and what we're going to go over, is a crude representation of what an ADC does. So the means through which an ADC takes that continuous value, turns it into a number, is through what's called an encoding scheme. So remember when we spoke about if we have a 1-bit ADC, so that would be my bit count. Let's replace this with an N. So if I have a 1-bit ADC, then the number of values it can have is 2. It's 2 to the power of N. If it's a 2-bit, the number of values it can have is 4. 3-bit, the number of values it can have is 8. Okay, so in our looking at how we can actually represent those values, then let's okay, so these are the 8 possible values my ADC can have. 1, 2, 3, 4, 5, 6, 7, 8. This is just for a 3-bit ADC. Okay, so this first one, 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1 here, or off, 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 on, on. Okay, so again, this is again a crude simplification of the way that ADCs work. Let's say that we've got our minimum voltage it can store and its maximum voltage it can store. Maximum voltage is going to be stored as the top value, and the minimum voltage is going to be stored as the lower value. And what it's going to do, there will be a series of steps in between. Okay, you will see that if you look up real encoding schemes for ADCs, often the lowest value has a slightly smaller horizontal space there, and the largest value has a slightly longer horizontal space. When we spoke about the resolution, okay, the resolution of our ADC, that is this value here. Resolution is the range divided by 2 to the power of n. N is the bit count. So we need something that can take those values that we've stored, okay, and convert them into these finite thresholded values. So we're going to try and do that. And I wrote a bit of code to do this yesterday, and I wrote it from scratch, so I'm glad it worked. And I'm going to try and explain what I wrote here. Okay, it's only about 8 lines of code, but it's pretty reasonable. Again, with most of these things, there's about 1,000 ways you could solve this problem, or 1,000 ways you could try and simulate this. This is just how I chose to do it yesterday. So we're going to look at that now. So I'm going to add this into here. So we've got our continuous signal, we've got our sampled signal with infinite value resolution. We're now going to look at then change the values according to the ADC thresholding. So the ADC can only store a finite number of possible values, so we're going to change them. So the things that we need to know are the bit count of the ADC, and we also need to know the input range, which I actually didn't include up here. So let's say up here, let's say input range of my ADC, and I'm going to say that this is 10, okay? Yeah, let's say 10, okay? And the way that I mean this is going to be, my ADC could store anywhere from -10 up to +10, okay? So actually the input range on this would be 20. That's just the syntax I'm choosing to use with this bit of code here, okay? How we work through it. So this means this ADC, if this were recording voltages, it could store anywhere from -10 up to +10, and then that would mean that the value A here, if I'm pointing at the right thing, would then be a 5 volts in here. Okay, so it needs to know that, and then we're going to change all of those values. So let's go back to the iPad actually. Let's have a look at that. So what that means is that this one for here, my Vmin would then be -10. My Vmax would then be 10 volts in this case. We're going to do a simplification of this stepping up here. We're going to make a set of values that exist at equal steps from -10 up to 10, okay? And equal steps of this here. Again, that's not quite how an ADC works, but it's good enough for our purposes to understand this thresholding. What this means is that anything below -10 would be stored as -10. Anything above +10 would be stored as 10. And then anything between is going to be stored as one of these finite values that we have in between. So what we're going to want to do, I'm going to want to take my sampled values and I'm going to want to add on to all of them the input range, and that's going to mean that then anything that is below the negative limit would then be a negative number. So let's do this. Let's say ADC signal is equal to sample values plus the input range. Is that right syntax? Yeah, input range. So that means that any values that were then lower than -10, which for this signal wouldn't actually be any of them just yet, would then become a negative number. And what I'm then going to do is I'm going to say anything. So in my ADC signal, any value that is lower than 0 is equal to 0. And that's going to say that any value that is then lower than this lower bound, I know has to be equal to the lower bound. And then I want to do the same with the upper bound. So this has now then changed all of my values into I've effectively, rather than going from -10 to +10, I'm now going from 0 to 20, okay? And this bit, I'm never going to examine this stuff. I just want to explain how this code works. If you're struggling with some of this, I'm happy to answer questions. But this stuff is a little bit beyond this course, but it's good fun whilst you're at home stuck in COVID and maybe want to learn a little bit of coding. So what I'm going to do is I'm going to take this as then now a vector of values that theoretically can go from 0 up to 20. I'm then going to take that and I'm going to divide it by 20, okay, or divide it by the maximum value. So we're non divide, it's easier to spell, divide by the maximum possible value. So I'm going to say ADC signal, and I'm going to divide it by the possible input range multiplied by 2. Now what that means now is that I've now got a vector of values that it goes from 0 to 1, so they are all decimal values. And so then the number of possible values that I could have is then equal to 2 multiplied by the bit count. Okay, so that's, no, bit count, I called bit count, not M. So M is just a number of the possible values that I can have. Okay, so that's going to, for a 3-bit ADC, this would then be 8. So let's change this, let's say ADC signal multiplied by M. Okay, so let's now, this looks like. Here we go. So I've now got what was, let's just print out these two things. Let's print out okay, so I'm printing out some. This original signal is then a big vector that goes and it's got negative values in. The ADC values that I've just taken are numbers, rather than going negative numbers, I've got decimals that go from 0 up to, well, the possible maximum would be 20 on here, but because my signal is quite low, I've got quite small numbers in here. Okay, because I'm actually only going from 0 to 5 here. So let's see what happens if I just change my input range up to 5 here. And we'll just run this again. There we go. So I've now got a bunch of decimals in here. Now what I want to do to these represent the finite number of values that I could have within here. So I then want to round these to the closest actual value that I could have. Okay, because anything that's actually a decimal in here is not a possible value that I could have here. It's just somewhere in between. So if I only, everything in here now needs to be rounded to the nearest number between 0 and 8 for my 2-bit ADC. Okay, so everything in here is a decimal, and these all represent values that are somewhere in between possible values my ADC can store. So I'm then going to round it using floor. I want to go to the lowest value below, because that's as close as that's sort of the closest we can simulate using the maths that we know to this representation here. So we're going to use that. Okay. Again, this is a simplification of what an ADC does, but it helps us understand it for our purposes. So we'll say round down. We're going to say ADC signal equal to mp.floor. There we go. So I've now just got a bunch of integers representing anywhere from those possible values that I could have had from my ADC. And then what I'm going to do is I'm going to divide them by the number of values to put them back into a decimal. That's going to be 8 divided by that, and I'm then going to multiply them by the maximum range. So m was the number of possible values. They're going to be decimals again, and I'm then going to multiply them by the maximum voltage range multiplied by 2. Why isn't it like that? Oh, because it's input range, not voltage range. Yes, it's input range, that's why. Okay, so I've now got this new thing here, which is my ADC signal. Let's just print it out and see what it looks like. Here we go. So it's only recording these discrete values of my actual signal here. Okay, so let's see what happens if we plot this 3-bit ADC representation on here as well. So I'm going to copy and paste one of these lines up here, remembering to copy all of them. So still sample time, and I just want to replace the sample values with here. And I'm going to replace this with if I run this, this should work. Here we go. Oh, I need to subtract the half the voltage on here. Okay, I still haven't done that on here, so let's subtract. Because up here, the very first thing I did was adding on the input range. So I need to record. I need to subtract that here. Oh, I'm glad that worked. Okay, so this now is the representation of my continuous signal, my sampled signal if I had an infinite value resolution, they're pretty good. And then this is if I only have a 3-bit ADC and I'm using my encoding scheme that I've sort of said is a simplification, but it's a pretty good estimation of what an ADC does. This is what that looks like. And let's just change the bit count in here. So bit counts, if I have a 2-bit ADC and I run this, we've got 4 possible values. And those are those 4 possible values here. Yeah. I can see this isn't, there's something not quite perfect in the way this works actually, and I can see how that works. I'm not going to bother changing it for our purposes because we'll see that when we increase this to a number like 5, we have a much better representation of what goes on here. Let's take it up to 16. Yeah, we can record some pretty good values as far as this goes now. Let me just see if there's a way I can get it to see if there's something I'm not copied down here. Okay, no, that's fine. That is fine. It's because I'm using the floor value there, using the floor function. Okay, so if we see here, if we change the bit count up to 16, these are so very close to each other that, let me zoom out again and move this around. If I get rid of the, here we go. Because 2 to the 16 is a pretty big number, let's have a look at this is. Okay, 65,536. We've got a lot of values in between there and there. But what I want you to look at, and what you're going to be asked to look at is, and what I want you guys to be aware of, so you've got the input range of 5 volts here, and we've got a voltage of 5 volts here. If I had, say, an input range of 10, which is actually what the input range of the ADCs that we use is, plus or minus 10 volts. Okay, that's the maximum we go up to. Probably shouldn't throw it around. Then if our amplitude of our input is quite significantly lower, so let's say the amplitude of our input is, say 1 millivolts, well, let's say 1 microvolt, so 1 times 10 to the minus 6, and I run this again, then I'm going to really mess up the recording there, because actually the threshold and the step between those values is so large, it's 300 microvolts, whereas if I change my input range here now down to say 1 or 10 microvolts, then yes, I would record this better. I would get better resolution there. So this is just showing you the implication of understanding how an ADC works. So if, for example, like let's say we were trying to record signals down in the millivolt range, and I had an input range set on my ADC of 10 microvolts, then here, my continuous signal is here, and my ADC is getting saturated all the time. And let's just change this up. Let's say I had an input range of, again, the same, these millivolts, and my input range of my ADC is 10 volts. Okay, my signal would be heavily thresholded according to the fact that my signal is not large enough to actually have a meaningful change on each of those quantas between those ADC bits. Okay, so this piece of code, what I want you guys to do is be able to produce this, and the last thing I want you to do is be able to print the based upon a given input frequency, given input amplitude, and then I want you guys to be able to reproduce some examples of aliasing and attenuation of your signals. So you need to be able to export these. Now the way that we export them is my figure.write, I think it's write image. I know this won't work. Try and do it as a PDF. That's because it's called my, yeah, why doesn't that not, why my figure? Oh, it's because it's up here, that's why it's saved. It doesn't know my figure existed only within this namespace up here. So if I run this, and now it returns my figure, let's say my figure. It's equal to that, and let's try and print this. So I'm going to print this using my figure.writeout. Yes, and I'm glad that didn't work. That's good. Okay, so I'm going to put this back. If I now try and run this, what I'm trying to do is I'm telling Plotly to print it out as a test out.pdf. And if I try and run this, it doesn't work because it says, let's go down, all of these errors are all sort of internal things within internal objects within Python. And it searched for something called Orca, and it doesn't know how to get Orca to work. So it tells me how to install it here. So it says if you haven't installed Orca here, you can do so using Conda. So if you don't know how to do that, you should have been watching some of those Python videos, but I will now install it. So annoyingly, my screen capture is not set up to record my terminal window, which is annoying, but all I'm going to go is into my terminal, and I'm going to type the line pip install Orca, and I'm going to type that in my terminal now. Slightly different syntax on Windows, but you guys should be comfortable with installing packages in Python, and if you're not, you should know where to ask for. But I'm just going to install that now. It's running, excuse me, it's running and it's installing, and it's just installed. And if I now try and run this now, didn't work. So let me try running conda install Orca, which is this line it tells me to do. Let's try. Okay, I'm gonna let this run, try and install on here. I know it works on my home computer. Don't worry about putting in PDF images on here. What you can always do in Conda, sorry, in Plotly, once you've got this image, you can then just click up here and you can download it as a PNG. Okay, I don't like downloading as PNGs because the bitmap images tend to be grainy at what we're looking at. So I'll try and include some instructions on the Slack site about how to get Orca to work so you can export these images, because that will be useful for you. But you can always just, for the purposes of getting your homework in, which you're going to be required to do, use this image and then use the up here, click on download as PNG. Okay, so you're going to be getting some instructions sent to you on Slack. Those are going to be a unique frequency you've got to look at, which is your input frequency for your continuous signal, unique sample rates, and then you're going to be asked to demonstrate what happens when you change the bit count, an example. Okay, and that will be coming to you this weekend, but you need to look at this notebook and get this notebook working, because this homework is going to assume you've gone through this lab and you have this notebook working. Okay, take care guys, see you all on Monday. Take care.